A very good afternoon to one and all. Welcome to Mybo Webinar-8. Myself, Sheikh Nasib Basha, Assistant Professor, G. Polarity College of Pharmacy. I am one of the core member of Mybo group. So today, last previous sessions, we have a various analytical experiments, analysis of variance in pharmaceutical experimentation and multiple comparison tests. So those have given by Professor J. Vijaya Ratna madam. And today also, we are here for the next webinar on Mybo Webinar 8 on chi-square test in pharmaceutical experimentation. So now I will invite our speaker, Professor J. Vijaya Ratna madam. Welcome, madam.
Thank you, Basha.
Professor J. Vijaya Ratna madam, retired professor from the AU College of Pharmaceutical Sciences, Andhra University. So I welcome you. It will give immense pleasure to introduce you, madam, to the Mybo webinar. So I welcome you, madam, to proceed for the further session of chi-square test in pharmaceutical experimentation. Now continue your session, madam.
Thank you, Basha. So it's a great pleasure for me to be talking to all of you. All of you are interested in learning a subject which is useful in pharmaceutical experimentation. So we have been giving seminars on how statistical concepts can be made use of, calculations can be done, which are useful in pharmaceutical research, either in pharmaceutical experimentation at B.Pharm or M.Pharm level or at PhD level. When we do certain practicals, when the results are obtained, how those results can be analyzed, how that can be useful in the field of pharmaceutical sciences, how statistics helps. This is the crux of our topic that we are handling. In today's class, I wish to tell you about chi-square test. So chi-square test in pharmaceutical experimentation is today's topic. I will be talking about a little bit about the theory of chi-square, how the test itself is carried out under various conditions, and how the problems are done in chi-square test and all that. So the procedure of chi-square test is used to test hypotheses about the independence of frequency counts in various categories. For example, the data may be the proportions of children and adults showing preferences for syrups, tablets, and injections. We record the number of individuals falling into each category, or we record the frequency. So we only have a few frequencies which constitute nominal data. With such data, the only analysis possible is to determine whether the frequencies observed in the sample differ significantly from hypothesized frequencies. So let me go back and explain this to you in an elaborate manner. So what is this test about? There are so many non-parametric tests in statistics. This is one of the non-parametric tests. What is a non-parametric test? A test to do which we do not need any parameter. What is a parameter? A mean, a standard deviation. These things are known as parameters. So to carry out the chi-square test, we do not need any parameter such as the mean or the standard deviation. And we do not need very rigorous basic assumptions such as in doing a jet test or t-test, which are parametric tests. We need the assumption that the basic population from which this sample has been taken belongs to a normal population. That type of rigorous type of assumptions are not there in chi-square test. So all that you need are numbers, properly categorized numbers are all that you need to do a chi-square test. So in this, we are finding about the independence of frequency count. By frequency count, we only mean a number. So under different categories, we have certain numbers. Are these numbers independent of each other, or are they dependent on each other? This is what we are finding out, determining in the case of chi-square test. For example, the data may be the proportions of children and adults showing preferences for syrups, tablets, and injections. While I was teaching chi-square test in my M-Pharm class, I used to really like one exercise I used to do. I used to, in a class of nearly 100 students, which used to be predominantly consisting of girls, but still there used to be about, let us say, 75 girls and 25 boys, something like that. In that type of class, I used to do this exercise, which used to be my favorite exercise. So what I would do, I would draw a table on the blackboard. So there will be 3 columns. First column is syrups, second column is tablet, third column is injection. And 2 rows, boys, girls. Then I'll tell my class, so definitely you have to take a medicine. Not taking the medicine is not your choice. So now you only have the choice of taking one type of dosage form, either syrup or tablet or injection. So then I would ask the class, how many of you like to take the medicine in the form of a syrup? I would tell the class, all of you close your eyes as I do this exercise. You will presently know why I asked them to close their eyes. So some of them will raise their hands for syrups. Then I'll count how many girls have raised their hands for syrups, how many boys have raised their hands, and I fill those 2 cells. Then I ask them, now bring down, and I also tell them some conditions. All of you have to close your eyes as you raise your hands. Number 2, you have to raise only for one, either syrup or tablet or injection, not for 2 or 3. Then I'll tell them, how many people would like to take this by tablet? Raise your hands. So girls and boys, they will raise. Again, I'll count and put the numbers in the cells. Then I'll ask them, how many of you like to take by injection? They raise their hands and I'll fill. Now 6 cells are there in the blackboard. All the 6 I'll count. What is the total number of girls under each, under syrups, under tablets, under injections I have. And in the row, I have how many girls are there in the class, how many boys are there in the class. Because each girl has to raise to something, each boy has to raise to something. So the sum total of the both totals will be equal. The total of the boys and the girls in the rows will be same as the total of the choice of syrups, choice of tablets, choice of injections in the column. So this grand total will be the same. Then, and now I'll tell you why I asked them to close their eyes. I asked them to close their eyes because each observation should be independent of another observation. This is one requirement. Each observation should be independent of all other observations. So what is possible is, suppose one girl named Mary is there. Mary raises for syrup. Then another girl will be there, Padma will be there. So Padma and Mary are friends. So Padma also may raise for syrup. That way, the assumption that the 2 observations are independent has gone. That's why one observation should not be dependent in any other way, in any manner whatsoever on another thing. So that's why another thing, that is one requirement. That is, each observation is independent of the other and they are also mutually exclusive. That means if somebody likes a syrup, that's all. He can't like tablet or injection. If somebody likes an injection, that's all. He can't like tablets or syrups. So this way, that classification should go. Now what do I have? I record the number of individuals falling into each category or frequency. So we only have a few frequencies which constitute nominal data. So whether they like the syrup or the thing is nominal data. That's all. Nominal means just a few categories. With such data, the only analysis possible is to determine whether the frequencies observed in the sample differ significantly from hypothesized frequencies. So next what do we do? This determination of hypothesized frequency or expected frequency is based sometimes on past experience, sometimes by fitting the data to a particular distribution, such as the binomial or Poisson. So I'll stay here once more and I'll finish this explanation. So what do I do now? In the 6 cells, I have certain observed frequencies. Next, I'll make the assumption. Now the hypothesis is being a boy or a girl or the gender of a person has nothing to do with the preference for syrups, tablet or injection. So the gender has no association with preference for syrup or tablet or injection. So if really my observation is right, that is the logic. If really my hypothesis is right, if gender has nothing to do with the frequency, with the number in the cell, then the total number of people who are preferring syrup should be equally distributed among boys and girls. The total number of people preferring tablets should be equally distributed between boys and girls. The total number of people preferring injections should be equal between boys and girls. Based on this logic, I'll calculate using a formula row total into column total by grand total. I'll calculate what is known as expected frequency in each cell. So each cell has an observed number, each cell has an expected number. This expected number is usually kept in the same cell with a red pen or something. Then what I'll do, observed frequency minus expected frequency, I'll calculate. I'll make a square of it and divide that by E. Observed frequency minus expected frequency whole square by expected frequency. Like this, I'll calculate for all the 6 cells and I'll make a sum of that value. That is the chi-square value. That's all. This calculation is so simple. Note the observed frequencies, find the expected frequencies by logic or by some mechanism, do O minus E, observed minus expected, make a square of that, divide by expected frequency. You will get a small value. So add up all those values to get the chi-square value. Now this chi-square value, you keep it, and at the given degrees of freedom, go to the chi-square table and find the criterion value. So write the criterion statement, and if your calculated value is below the chi-square value, accept the H naught. If your calculated value is more than the table value, reject the H naught. This is all. Then that based on that, you take the decision whether gender and choice of a formulation are dependent on each other, associated. And to my surprise, every time I did this exercise in my class, I used to find that yes, gender has an association. In a very simple small size sample like 100, I used to get this result. Girls used to prefer more syrups and boys used to prefer more injection. So this type of thing is there. We think all these are just our prejudices. That's not right. Certain things are there. So I used to find in a small class itself this type of preference. So to make a simple decision with a simple numbers, then chi-square test is your choice. So a non-parametric test is very easily done. Easily done. Sometimes just with the help of a hand calculator, you can quickly do the analysis. That is the advantage of chi-square test. So this determination of hypothesized frequency or expected frequency is based sometimes on past experience, sometimes by fitting the data to a particular distribution, or sometimes based on certain logic. In the example I just now gave you, I use some logic. I said they should be equal. Sometimes we depend upon past experience. Now suppose I say that from my past experience, the girls' preference is this, boys' preference is this. So that will help me do the calculation of expected frequency. So sometimes we use distributions like binomial or Poisson. Sometimes we use some simple logic. So how you calculate the expected frequency is the only point of difference in the way you are testing for calculation of chi-square. These two uses of the chi-square are called goodness of fit tests because they tell us how well an observed distribution fits a hypothesized or theoretical distribution within a single population. So these two uses will tell us what goodness of fit. These are known as goodness of fit tests. A third use of chi-square. So we talked about two uses, past experience, binomial distribution. These are goodness of fit uses. A third use is that the same proportions will be found in 2 or more populations. So just now the example I gave you regarding gender preference for formulation is that Same proportions will be found in 2 or more populations. For example, we can take 2 groups of patients. One group receives a treatment and the second group does not receive a treatment. We can now compare the proportion of people cured in both the groups. It is the famous case like cases and controls. You can take cases who are having cases and controls, both may have a particular disease. Let us say a dermatology issue. Cases prefer to take no treatment. We won't take any treatment. Cases take the treatment, controls do not take any treatment. So how many among the cases got cured? How many among the controls got cured? Cured, not cured. And cases and controls as the rows, cured, not cured as the columns. You have a contingency table and you can work out the chi-square. So test of goodness of fit for one-way classification or for one variable only. So this test of goodness of fit, wherein you are putting the data to a binomial or Poisson distribution or by some logic to some distribution, is a one-way classification. Test of independence of attributes for more than one row or column in the form of a contingency table concerning several attributes. These are different uses. So when we say use the word test of independence of attributes, we find out whether whether numbers that have come into different cells are they independent or they dependent on each other. So the test of population variance through confidence interval suggested by chi-square test is one use, and test of homogeneity of the data. All this data, is it homogeneous or is it belonging to different populations? These are also different types of chi-square tests. So let us look at certain properties of the chi-square. This is what I am calling as a theory. The chi-square statistic is used to test the statistical significance of the observed association in a cross tabulation. A cross tabulation is like a contingency table which has rows and columns. It is used to test the statistical significance of the observed association. When there are 2 items in the columns, 2 items in the rows, like cases and controls in the rows and cured and not cured in the columns, is this categorization of cases and controls reflecting in the categorization of cured and not cured? Is there any association or is there no association? This is what we are testing in the chi-square test. So this assists us in determining whether a systematic association exists between the 2 variables. So the chi-square test, let us see its probability curve, characteristics, assumptions and advantages. Let us see what they are. So the chi-square distribution is a skewed distribution whose shape depends solely on the number of degrees of freedom. As the number of degrees of freedom increases, this distribution becomes more symmetrical. Presently we'll see the curve, then you will understand better. There is a chi-square distribution for every number of degrees of freedom. The following diagram shows various chi-square distribution curves corresponding to the number of degrees of freedom 2, 5 and 10. See, now these diagrams have been developed with the help of the probability theory. So they say that, see, this is what we mean as skewed. Skewed means it is not symmetric. See, this is almost a bell-shaped curve, but this part is skewed. This is different. What is not skewed? What is symmetric? A bell-shaped curve which you see in the case of a normal curve is not skewed. Normal curve is bell-shaped. It is not skewed. On both sides, it is going in the same way. So that type of normal distribution is the basis for parametric tests like Z test and T test. The T distribution itself is a little bit not as good as the normal, but as the number approaches 30 and above, the T distribution approaches to the normal distribution. Now, let us look at the chi-square distribution. For a degree of freedom of 1, see how that is happening. The relative frequency. See, the relative frequency which is there on the y-axis, the relative frequency, that is the possibility of the numbers or the relative frequency is coming down like this. Slowly it is going nearer and nearer to the x-axis in an asymptotic manner. So the relative frequency of the chi-square value is coming. So df3 is the chi-square value is changing like this. For degrees of freedom of 3, the chi-square value, the relative frequency of the chi-square value is going like this and is coming down like this. Now, as the degrees of freedom are increasing from 5 to 10, the chi-square value possibility relative frequency is going like this. More and more you are getting not exactly a bell shape, but more and more sort of normal. It is becoming flattened like this. So for degrees of freedom 10, it is like this. So there is only one thing which determines how the chi-square value goes. How the value of the chi-square, what is the possibility of the chi-square value being in a particular range. That depends on only one, that is the degrees of freedom. So, for example, for binomial, there are two requirements, mu and sigma define that, like that. But chi-square distribution is determined only by the degrees of freedom. There is nothing else which determines the chi-square. So some important properties of the distribution are given here, what I just now told. For n is it greater than 1, as chi-square increases, probability of chi-square decreases rapidly and finally tends to 0 as chi-square approaches to infinity. Let us focus on this sentence. As chi-square increases, the probability of the chi-square decreases rapidly and finally tends to 0. So for n greater than 1, the probability as chi-square value increases, the probability of that decreases like this. So till a little point, the probability of the chi-square value increasing is increasing. Then it goes on decreasing. For the n is equal to 1, it goes on decreasing only. So here the point to be seen is, as chi-square value increases, its probability is decreasing rapidly. That means the probability of a high chi-square value is not so high. As the degree, depending on the degrees of freedom, certain chi-square value is possible. So for the chi-square value to be very high, probability is not very high. As the chi-square value is increasing, its probability is decreasing for a given degrees of freedom. So this is how the table, if you look at the table carefully of a chi-square table, you will understand what I am saying. So as for a given degrees of freedom, as the value is increasing, its probability is decreasing. So they always tell, when you are doing the chi-square calculation, if you get an absurdly big value in hundreds, something like that, be very, very conscious. Such things are not usually possible. That's what they tell. Therefore, for n greater than 1, the chi-square probability curve is positively skewed towards the higher values of chi-square. So here what's happening? For a given degrees of freedom like 3, as the chi-square value is increasing, its probability is decreasing. Initially, it is increasing. So the probability of the chi-square value is gradually decreasing. So this is what. Then the mean of chi-square distribution is equal to the number of degrees of freedom. So in this distribution, there is only one important issue, that is the degrees of freedom. The degrees of freedom is equal to the mean. So how are degrees of freedom obtained? We'll come to that. If suppose r minus 1 into c minus 1, that is the way. Suppose there are 2 columns and 2 rows, 2 minus 1 into 2 minus 1, that is equal to 1. So that is the way we calculate the degrees of freedom. The degrees of freedom usually tell us how much we can maneuver with respect to the numbers. For example, talking about the 2 into 2 cell, where there are 4 numbers, we all know that. So the row totals are given, column totals are given, grand totals are given. As a result, if you just put one value in one cell, all other 3 are already determined. That is why degrees of freedom is 1. Because row total, column total are all fixed. If you put one value in one cell, all other 3 are already fixed. That is why degrees of freedom is equal to 1. So the degrees of freedom indicates the freedom that we have to maneuver with respect to the numbers. So the curve shows a fast approach to symmetry as the number of degrees of freedom increases. That is what you see here. So this is not at all symmetric, a little bit symmetry, more and more symmetry, more and more flattening at the top, and more symmetry is there as the degrees of freedom are increasing. The smallest possible value of chi-square is 0 and the largest value is infinite. See, chi-square, when can chi-square value be 0? I told you O minus E whole square by E. Sigma of O minus E whole square by E is equal to chi-square. Sigma is the sum of all the 4 cells. Right now we are talking about 4 cells question. So if suppose O minus E is equal in all the 4 cells, then all are 0, then chi-square is 0. So if O, suppose the more the difference between O minus E, observed and expected, a lot of value is possible. But I already told you, beware of very large values. They don't usually happen. Something may be wrong with respect to your either noting the values or calculation of the value. So smallest possible value of chi-square is 0 and the largest possible value is infinite. So now the definition of chi-square, a test statistic which measures the discrepancy between observed or actual frequencies O1, O2, On and their corresponding expected frequencies E1, E2, En is called the chi-square statistic. We obtain chi-square by using the formula chi-square is equal to sigma of OI minus EI whole square by EI. As I told you, please see, here it is explained, expanded. O1 minus E1 whole square by E1 plus O2 minus E2 whole square by E2 plus so on On minus En whole square by En. So what are we doing? In every cell, we note the observed frequency, we note the expected frequency, square divided by E1, corresponding E1. This and this are same. So like that we do in each cell and we make a sum of them. Then the characteristics of the chi-square distribution are like this. This test is based on frequencies or events, whereas the Z and the T are based on parameters like the mean and the standard deviation. So the Z and the T are done based on mu and sigma, mean and standard deviation. But chi-square is based upon frequencies, on numbers. Always remember, only numbers have to be taken, never percentages. Don't ever take percentages for chi-square. You will get all wrong values. Just to take the numbers as you record them. Although the chi-square distribution is continuous, it is applied to discrete variables whose frequencies can be counted and tabulated with or without grouping. So this is a continuous distribution, but still we work with discrete variables like what? Like this, preference for a syrup, preference for a tablet. There is no continuity there, they are discrete, and yet we can work on that variable. Liking for syrup or tablet or injection, a discrete variable, but still we do chi-square on that. This distribution is similar to the T distribution where the critical values vary with the degrees of freedom. Just like in the T distribution, the critical value that you get in the table is dependent on the degrees of freedom in both T and chi-square. So the assumptions are the application of chi-square test assumes that the observations recorded are collected on a random basis. So basically the sample that is taken should be in a randomized manner. If you are taking in a non-random manner, that will not work out. For example, suppose I take the opinion of all children in one case and all old people in one case with respect to my syrup, tablet and thing, that will be an obviously biased type of thing. So unless the observations are recorded in a random manner, this thing will not work out. That means if there is a particular systematic error in the practical recording, it will not work out. That the outcome of each observation is independent of the previous outcome. So each observation is independent. It is not dependent on other observation. Because observation 5 is something, observation 6 should not be altered. All observations should be independent. The events for which the test is used are mutually exclusive. Each event is mutually exclusive. Mutually exclusive means either syrup or tablet or injection, not all. Either head or tail. If it is a head, it cannot be a tail. If it is a tail, it cannot be a head. That is mutually exclusive for you. So they should be mutually exclusive and independent of each other. The total number of observations should be large, say more than 50. Then only it will work out. Usually in pharmaceutical experimentation, you should be observant of this type of thing. See, in clinical research, you are working with 50 patients, 100 patients, like that. In that type of situation, it is okay. It will work out. But if you are working like in your pharmaceutics in vivo experiments, where you are working with 6 rats or 10 rats, then in that type of situation, chi-square will not work. Only when the numbers are large, then only it will work. Then, when the number should be large and in no cell, the frequency should be less than 5. Then only this will work. So, the frequency of each cell should not be less than 5. Since the chi-square distribution is a continuous distribution, it cannot maintain its characteristic of continuity if cell frequency is less than 5. The pooling is done if cell frequencies are less than 5. Suppose there are some 6 or 8 cells in a particular chi-square contingency table. In one cell, the frequency is 3 or 4. Then what we do is, we close that cell and we join that cell to that frequency to another cell. So this is known as pooling. This is possible in only certain situations. So in no case should frequency be less than 5. If it is less than 5, that continuity is not there on continuity is not there and in such cases continuity is not there, and in such cases we do pooling. So the data should be expressed in original units and not in percentages or ratios. So we cannot put them in percentage or ratio. The chi-square test is a non-parametric distribution-free test. This we should all remember. This is not a parametric. Often it is taught along with Z and T and F. So people think it is parametric, but it is not. It depends, the chi-square value depends on only one thing, that is the degrees of freedom. It does not depend on, there is no question of any mean value or no question of any parameter. It does not depend on any distribution. So it is called as a distribution free test. So the advantages of the chi-square are, there are no rigid assumptions are necessary. In most of the parametric tests, rigid assumptions are necessary. It is not necessary to calculate mu or sigma. Degrees of freedom are sufficient. Simple to understand, no mathematical details involved. Here there are no equations, no derivations. So it is very simple, concept is simple. Are the observations, observed frequency, expected frequency? Is the difference more or less? That's all the concept that you need to understand. It is used in simple ranking of values and useful where data is not exact. Can be used with very small samples and is therefore useful in medical and social science research. By very small, we mean 50. We don't mean 5 or 10. So chi-square test is extensively used in clinical research and also in social science research, because you can work with 50 number of people, something like that. So the chi-square depends on the degrees of freedom. When the observed frequencies can be listed along one dimension, row or column, they are k minus 1 degrees of freedom, where k is the number of categories of observed frequencies. So if there is only one dimension, that is, you as a column you are putting or as a row you are putting, then degrees of freedom is k minus 1. For a contingency table with r number of rows and c number of columns, the degrees of freedom are r minus 1 into c minus 1. The number of rows minus 1, number of columns minus 1. In the example that I was talking about, we had 2 rows, boys and girls. And so rows is 2 minus 1. We had 3 columns, syrups, tablets and injections. That is 3 minus 1 is equal to 2. So 2 into 1 is equal to 2. So the degrees of freedom in the example that we are talking about is equal to 2. So the method of testing is the same as per other tests. So okay. So there is what we call as the general testing procedure. This general testing procedure is the same, whether you are doing Z test or T test or F test or chi-square test or any other non-parametric test such as the sign test or the rank test or rank sum test or median test or run test or analysis of variance. In all these cases, you follow the general testing procedure. So that testing procedure consists of this. Number one, state the null hypothesis and the alternative hypothesis. Null hypothesis is also called as H0. Alternative hypothesis is also called as H1. So the null hypothesis is always a statement of nil difference. We write mu1 is equal to mu2 or x bar is equal to mu. Suppose we have drawn a sample and we are finding its equivalence to the population, then we write x bar is equal to mu. Suppose we are saying two samples are equal, mu1 is equal to mu2. But the alternative hypothesis contradicts the null hypothesis. In the alternative hypothesis, we write if there are more than two mu's, we write all mu's are not equal or mu1 is not equal to mu2. Like this, null hypothesis and alternative hypothesis are contradictory to each other. You definitely have to write these things when you are working out the problems either in the classroom or in the examination. Definitely there will be marks allowed to each step. Then you have to write the level of significance alpha, either it is 0.05 or 0.01. What is the level of significance? This level of significance is indicating the probability level at which you are considering the null hypothesis. So when you say 0.05, you say that among so many number of practicals, if the practical is repeated so many times, let us say 1000 times like that, in such a case, what is the probability of getting this much value of chi-square, in this case chi-square. So at this probability level, at the given degrees of freedom, you will go to the chi-square table and find the value. That value of chi-square is the possibility of that value for that given degrees of freedom. When you go back to this and see this, so here this curve is telling you the probability of a particular chi-square value for that given degrees of freedom. That probability we are taking as 0.05. At 0.05 probability, what is the possibility of getting this much of chi-square value? So then state the 0.05 or 0.01. 0.01 is more rigorous than 0.05. Suppose the difference between observed and expected is quite large and the chi-square value expected is quite large, then to increase this level of significance also indicates the confidence with which we are speaking with respect to our result. The more the difference between the old and the new, and the more the difference between observed and the expected, the more our confidence. So in a certain case, we can take 0.01 also. If something is rejected at 0.01 also, that means it is very good. That means the difference is quite lot. State the criterion, that is the chi-square value at the given alpha and the given degrees of freedom from tables. So look at the critical value and write the criterion statement. What is the criterion statement? If the chi-square value obtained from the calculation is more than the table value, we reject the null hypothesis, otherwise we will accept it. That is the criterion statement. So before we do the calculations, we have to write all these things. Write the observed frequencies. Calculate the expected frequencies by one among three methods: from past experience, by fitting a distribution such as binomial or Poisson, by assuming that there is no association. Calculate the formula chi-square is equal to sigma of O minus E whole square by E. So this is how, by any one of the three methods, either from past experience. From past experience, suppose my idea is that, or from past experience, I am telling that about 20 girls will prefer this, 30 boys will not prefer this, something like that I tell. So that becomes my, on that basis, my expected frequency will be calculated. Or we fit a binomial equation, we will put our Poisson equation we'll put and find out the expected values. Or assuming that there is no association, by using a simple formula like row total into column total by grand total, we find out the expected frequency. So from that we calculate O minus E whole square by E. We make a sum of all of them and calculate the chi-square. So we compare the computed value with the criterion and take a decision. This is the testing method. So let us take one example after the other for different positive tests and see how chi-square is done. So a marketing research department of a pharmaceutical company has chosen 7 cities. It is believed that each city has the same sale potential. The actual number of drug products sold in a day by the company in each city is given in the table below. We have to test the hypothesis that the 7 cities have equal sale potential using a level of significance of 0.05. Now let us first of all understand the problem. It is very important always to read the problem a number of times so that we understand the context and the problem properly. So what is this? There is a marketing research department in the pharmaceutical company. They are selling in say 7 cities. Let us say Hyderabad, Bangalore, Bombay, Delhi, Calcutta, Chennai and Mysore. So 7 cities they have taken. The idea is that in all the 7 cities have the same sale potential. So as per that, from on every given day, say Sunday to Saturday, in each city, each day by evening, how many products are sold? They will calculate. So as per their assumption, the number of products sold at the end of each day from every city should be same. You can't expect them to be exactly identical, but in the long range, more or less they should be same. There should not be a wide difference between them. So that the concept is that the sale potential is the same. So actual number of drug products sold are the observed frequencies. Test the hypothesis that 7 cities have equal sale potential using level of significance of 0.05. So first of all, we have to write the null hypothesis, that is all cities have equal sale potential, that is all mu's are equal. Then alternative hypothesis is all mu's are not equal. Then level of significance is 0.05. Then critical value you have to write. So this is a single column type of distribution. So k minus 1, the degrees of freedom are k minus 1. So 7 minus 1 is 6. So at that degrees of freedom, we have to go to the chi-square table at 0.05 and determine the chi-square value. We have to write the critical statement. Then we have to find the expected frequency, O minus E whole square, make a sigma of that. So that is the procedure. So these are the numbers given in the problem. So from A city, 120 products are sold, B 185, C 260, D 190, like that. So every city has given the number of drug products sold in a day. On a given day, on one day, it is not on Sunday to Saturday, I am sorry. On a given day, from one city 120, another city 185, another city 260, another city 190, like that, different numbers are there. Then how do we do the problem? All the cities have the same sale potential, null hypothesis. The cities have different sale potential. All mu's are not equal. You have to write in both ways, symbolically also, words, sentence also. All mu's are equal here, all mu's are not equal here. Then alpha is equal to 0.05. Criterion, table value of chi-square per 6 degrees of freedom is 12.59. Criterion statement is, if the calculated value of chi-square is more than 12.59, we reject H0, otherwise we accept it. So this is how we work out. These are the observed frequencies. Then the logic is like this. If nearly all the cities have the same potential, then if you take the sum of all the values is 1400. 1400 by 7 should be sold from each city. This is the logic. So if really there is no association between one city being more and the city being less, if you take the sum of all the values, that is 1400, and divide by the number of cities, that is 7, that should be the frequency from every city, 200 each. Then you take the difference between observed and expected. 120 minus 200 is equal to minus 80. Now you make a square of that and divide by E. E is being minus 80. So O minus E whole square by E. So because you are making a so this is how you do the O minus E whole square by E. This is how you get it, and the chi-square value is equal to 73.25. So this is how you get it. Now, since the computed value of 73.25 is more than the table value of 12.59 at 6 degrees of freedom and 0.05 level of significance, reject H0. The sale potential of the cities is different. This is how we make the conclusion. So, this is the decision. This is the sale potential of the cities is different. This is how we calculate. So then, test of independence of attributes is the one which we have showed is the test of goodness of fit. Then we can read about the test of independence of attributes and the contingency by doing the contingency table. So the test of independence of attributes, in the previous example, we calculated the expected frequency based on some assumption, but sometimes there is no basis whatsoever for formulating an expectation. In such a case, we form contingency tables. So a double-blind experiment was conducted with 145 subjects to find out whether or not caffeine delays the onset of sleep. The results are shown in a table below, contingency table below. So usually, this is how the data are given. So what is that? 145 subjects were taken. This is a double-blind experiment. What is the meaning of the double-blind experiment? Now they are giving caffeine. How they must have given caffeine? Maybe they gave some coffee or something, so that to find out whether that coffee is causing a delay in the onset of sleep or not, they wanted to find out. So maybe they are giving to all 145 people. Total 145, placebo is given to 73, caffeine is given to 72. Total 145 people are given something to drink. They could not have known, all the 145, they do not know what they are taking. Whether they are taking coffee or not coffee, they don't know. Similarly, the investigator also does not know what he is giving. They are properly coded and given. Then all the 145 subjects are studied to find out whether there is onset of sleep is delayed or not. That is how they have found out. And then the results are given below. So delay with placebo, delay is seen in 8 people. With caffeine, delay is seen in 30 people. With placebo, no delay in 65 people. With caffeine, no delay in 42 people. So this cell frequency is usually called as A. This cell frequency is usually called as B. This is C, this is D. The column totals are this. The row totals are this. The total is always same. Row total as well as column total is the same. So, in this example, consumption of caffeine has no association with delay in sleep is the H0. H1 is consumption of caffeine has an association with delay in sleep. So, alpha is 0.05. Degrees of freedom is R minus 1 into C minus 1 is equal to 1. See, in this is the minimum type of, smallest type of contingency table. So, in this, you have only 1 degree of freedom. So the criterion, the table value of chi-square at 0.05 for 1 degrees of freedom is 3.841. Now these small things, what I mean is, this 1 degree of freedom in a 2 into 2 contingency table comes so many times that you remember these values, you don't even go to the tables. 1 degrees of freedom is 3.841. And the criterion statement is, if calculated value of chi-square is more than 3.84, we reject H0, otherwise we accept it. So the degree of freedom is equal to 1. For any one among the 4 cells is fixed, all the other cells are fixed. I already told that. So see, these totals are fixed. As a result, if you fix 8, then 38 minus 8 is equal to 30, and then 73 minus 8 is equal to 65, and 107 minus 65 is equal to 42. So if 1 is fixed, all are fixed. That is the meaning of the word. So, if placebo and caffeine are really similar, then the proportion of subjects showing a delay will be the same in both the groups. This is the logic. The logic. Earlier, remember, I said, if really all the cities are same, the sum total of the products sold divided by 7 should be the expected frequency from every city. Similarly here, if really placebo and caffeine are really similar, if caffeine really has nothing to do with the onset of sleep, then the proportion of subjects showing a delay will be the same in both the groups. I'll explain this even better. Take this, delay in sleep. Among 140, delay in sleep is 38. Among 145 subjects studied, 38 people showed a delay in sleep. If really caffeine has nothing to do with placebo, the proportion of people showing delay, what is the proportion of people showing delay? 38 by 145. Should be the same among placebo taking people and caffeine taking people. Based on this logic, we are calculating the expected frequency. 38 into 73 divided by 145. So this is the logic. So cell A should contain 73 into 38 by 145. Here I have written, that is how it should be written. 73 by 145 into 38. So the delay is shown by 38 people. So 38 by 145 into 73. Anyway, it is the same. Row total into column total by grand total. That is the way we work out. So 19.1. So once 19.1 is fixed, all others are fixed. Why are the others are fixed? So here 19.1, 38 minus 19.1, 19.1 is coming here. 38 minus 19.1 is this value. 72 minus that value is this value. Like that, we'll get the values of all that. We can also calculate. For each, we can write row total into column total by grand total, or we can find out like this. By subtraction, we'll get B is equal to 18.9. B is equal to 18.9, like that. We do that. So what most of the time in the regular work, what we can do, in the calculation using a calculator, we can use this. But because we are talking about human beings or sometimes animals, because they are individual units, we write this as 19, 54, 53, such that the total is not affected. We can remove the decimal value because we are talking about individuals or animals. Then what we do? O minus E whole square by E. So 8 minus 19.1 whole square by 19.1. Like that we do, and the value is 6.45. So B value is 6.51. So like this we write for C and D, we calculate O minus E whole square. 65 minus 53.9, some value is there, whole square divided by 53.9. 42 minus 53.1 whole square by 53.1. This is minus 11.1 whole square by 53.1. So this is how we get the values. So here this minus value has come, by squaring that minus value has gone. So you are always getting positive values. There is no problem there. So the chi-square value is obtained by making the sum of all the values. Sigma O minus E whole square by E. 17.56 is the chi-square value. We therefore reject the null hypothesis and conclude that the caffeine did significantly delay the onset of sleep. And conclude that caffeine did significantly delay the onset of sleep. So caffeine is there in the onset of sleep. It caused a delay in the onset of sleep. Sometimes we get an idea by looking at the numbers itself. We feel, see, the numbers difference is quite large. 30 is much larger than 8 and 65 is much larger than 8. in the case of placebo. In the placebo, only 8 people had a problem, had delay. So numbers also tell us, but the statistic calculation will clearly give us the proof, and we can tell statistically there is significant difference, and we prove our conclusion statistically. Here there is another point that we have to look. So there is the concept of Yates correction, and a 3 into 3 contingency table is what we are going to study. What is this Yates correction? In a 2 into 2 contingency table, that is, what is a 2 into 2? Just now what we have seen, caffeine, placebo, delay, no delay, is a 2 into 2 contingency table because there are 2 rows and 2 columns. The number of degrees of freedom is equal to 1. If any one of the observed cell frequencies is less than 5, the use of the pooling method will result in a degree of freedom of 0, which is meaningless. Hence, we carry out a correction called Yates correction for continuity. Let me explain by showing this cell again to you. So suppose this is 3. Suppose those who took placebo, only 3 people had delay. So we should not use the chi-square formula when any cell is less than 5. Then what you have to do? By pooling method, you have to merge the A cell with the C cell. Then necessarily B is also. Then what will happen here? The degrees of freedom will be 0. There will be only one row. Degrees of that is not anyway possible. It should be like this only. So 0 is meaningless. So what do? We do Yates correction for continuity when there are 2 into 2. In all cases, when there are 2 into 2, we carry out Yates correction. Even when you feed your data into the computer, it will give the chi-square value normally, and with Yates continuity correction, it will give. There will be a small difference between the chi-square value, which I have obtained normally, and the one which I have obtained with Yates continuity. So in Yates continuity, what do? There is a formula. We add 0.5 to the cell frequency which is less than 5, and then adjust the remaining cell frequencies accordingly. So the total should always be same. Total should never be different. Suppose this is 3. Then we write this as 3.5. Because this has increased by 0.5, this is reduced by 0.5. Then this is increased by 0.5. Then this is reduced. Because this is reduced, this should be increased. None of the totals should change. So if you add 0.5 here, you subtract here, and you subtract here. Then everything will be the same. If you are adding here, you subtract here, you add here, you subtract here. So this is how all totals are same. This adding of 0.5 and subtracting of 0.5 to compensate for something being less than 5 is known as Yates correction. So it is done normally also when cell frequencies are more, also when there are only 4 cells. But definitely if one cell frequency is less than 5, you have to do Yates correction. The chi-square test for a 2 into 2 contingency table is indicated below. Numerator is n into AD minus BC whole square. Capital N is the total number of observations. A is the number 1 cell. B, these are the observations in the cells. You have seen first cell is B, first cell is A. You have seen here A, second is B, C, D. With this nomenclature, then you are having the formula is chi-square is equal to n into AB minus BC whole square divided by A plus C into B plus D into A plus B into C plus D. Degrees of freedom is equal to 2 minus 1 into 2 minus 1 is equal to 1. So, in fact, using this formula is so easy. I always tell my students to use this formula when there is a 2 into 2 contingency table. Instead of that can also be done. O minus E whole square by E can also be done. Instead of doing all that, straight away substitute by numbers in this. No need to calculate any expected frequency. Just substitute your numbers in chi-square is equal to n into AB minus BC whole square by this, and you get, after Yates correction, the formula is chi-square is equal to this. Let us see how this is done. According to Yates correction, we subtract and add 0.5 in this manner. So an investigation was made into total, another example I am giving. was made into fatal poisonings of children by 3 drugs, which were the leading causes of such deaths. In each death, an inquiry was made as to how the child had received the fatal overdose, and the responsibility for the accident was assessed as in the following contingency table. First of all, understand the problem. Children somehow took the poison. The poisoning was fatal. Then, by 3 drugs, A, B, C, 3 drugs. So, this type of overdose or poisonous dose, how the children got access to that? Is the child responsible, or is the parent responsible, or is someone else responsible? That responsibility was fixed, and the numbers are given like this. 3 drugs, child, parent, another person responsible. So, totally 102 were tested, and the frequencies are given. These are the observed frequencies. Child is responsible in the case of drug A is 8, 12, 13. Parent 17, 10 and 9. Another person 14, 9 and 10. Is it that there is any association between the drug and who is responsible, or are they independent of each other? That is what we have to test. We write the null hypothesis. The apparent associations between the different groups are due to chance, not due to any real reason. Alternative hypothesis, the 3 drug fatality groups represent the same population. Level of significance is 0.05. Degrees of freedom is 3 minus 1 into 3 minus 1. 2 into 2 is 4. Chi-square value is, at that degrees of freedom, it is 9.5. The criterion statement is, if calculated value of chi-square is more than 9.5, we reject H0, otherwise we accept it. So the chi-square value, if there were no associations, the proportion of drug A caused deaths would be the same in all the 3 fatality groups. So by using the logic, if really there is no association, the proportion of the drug A caused death would be the same in all the 3 fatality groups. So this is the same, row total into column total by grand total. 39 into 33 by 102. See, 39 into 33 by 102. 36 into all 3 will be calculated. So 33 into 39 by 102 will be the expected frequency that is to be recorded here. So what I advise you to do, what I used to tell my class students to do is, we put a box here, and I tell them to bring another color pen. So with a green color pen, they will record here the expected frequency, like this, a small cell here, a small thing, and like that they will record. For this, it will be 33 into 31 by 102. For this, 33 into 32 by 102. We'll write. Then 36 into 39 by 102. 36 into 31 by 102. 36 into 32 by 102. Like that, we calculate for every cell the expected frequency and write it in the concerned cell only. What would be the next step? Suppose this is 10. This 10 is expected frequency, 8 is observed frequency. Then 8 minus 10 whole square by the 10. Like that, we calculate the O minus E whole square. So we have written the initial statements. Now we are calculating the expected frequency. So this is how 12.6 is the expected frequency. 10.4, like this we write the expected frequencies. Then chi-square is done by 21.2 by 12.3. So this is the O minus E whole square by E. O minus E whole square by E. Like that, for all the 9 we calculate, and the total is 4.28. So 4.28 is less than 9.5. So we accept H0. There is no association between the different fatality groups and the drugs. So in each drug case, who is responsible? Really, there is no association. So that is the conclusion we got based upon the chi-square test. So here 4.28 is less than 9.5. So we accept the null hypothesis. So this is how in different cases we have seen. So far I have shown this is a 3 into 3 contingency table. I have shown you a 2 into 2 contingency table. So please remember that I have shown you goodness of fit. Goodness of fit I have shown with the help of the example of 7 cities having the same sale potential or not. That question. So that we have done based upon logic we have done. Then we have done another problem on caffeine delay or no delay. Then child who is responsible, like this. So we have done the goodness of it, and we have done the independence of attributes. Let me take you back again once to the first few slides where I was telling you about the uses of chi-square. So here I was telling you, yes, these test of goodness of fit for one-way classification for one variable only. This we have seen with the example of the 7 cities. I told you we can either use binomial or Poisson or some fit with the help of reasoning. That is what we have done. Then the test of independence of attributes for more than one row or column in the form of a contingency table concerning several attributes. This also we have seen with the help of the caffeine example, and just now the 3 drugs and the 3 fatality groups example. Now, the third use, test of population variance through confidence interval suggested by chi-square test, I have not taken, I am not doing. Similarly, test of homogeneity also we are not taking. So these type of problems also crop up in type of research work and in certain situations, and usually at the level where we are working, neither in research nor in experimentation we get that type of situations. So I am not going into that. We have tested for 2 varieties of uses of chi-square. So the difference comes only in the way how you calculate the expected frequency. So all this we have covered. Yates correction also we have seen. So Yates correction for continuity is done when there are 2 into 2 tables, and definitely if one cell frequency is less than 5. So now I am showing you one application that was there in the case of one of the research scholars' work who worked in a hospital. This candidate has taken psoriasis patients as cases and dermatology patients without psoriasis as controls. He wanted to he studied the serum triglyceride. He took blood samples from all the 264 patients. From all of them, he has taken blood samples. He has determined triglyceride values and he has recorded them. And he classified the triglyceride values as more than 150 mg per dl, as less than 150 mg per dl. There should not be a high value. High value is always dangerous. And so he has recorded how many among the controls have high triglyceride and less. So there is a 4 into 4 among the cases, that is psoriatic patients. How many have high triglyceride? How many have less triglyceride? Among the controls, that is dermatology patient but not psoriatic patient, how many have high triglyceride? How many have less triglyceride? Now, as I told you earlier, the numbers itself give us a feeling. The high triglyceride is 102. Here, 30 people only have less triglyceride among 132. Among the controls, only 55 have high, 77 are low. But we can do the chi-square test. See, when this triglyceride distribution is distributed across, say, a low value of 50 to a high value of 400, this result will not come like that. But the minute we make it into a binary classification, more than 150, less than 150, the result jumps at us. Look at this. These are the marginal totals. These are the column totals. Grand total is 64. Chi-square test statistic problem is done. This was done in the computer and the value is 34.71 and the probability is very, very low, 0.0000 something. So the result is significant at p is less than 0.05. If this value is less than this value, then you can declare. Then till now, in all the problems that I am telling you, go to the table, find the test statistic. If your calculated value is more, you reject. If it is less, you accept. That is one way of taking the decision. Now, most of the things you see in research papers or in thesis books or what the computer gives is like this. It gives the probability value. What is the meaning of this? The probability of this much high chi-square value coming due to chance is very, very low, 0.000 something. This value coming due to chance is very, very low. That is why it is very significant. Because this value is high, it is significant. And it further tells the chi-square statistic with Yates correction is 33.25, a little bit less. This is 34, this is 33.25. The p-value is still high, it is significant. This is how the computer will give you when you feed the values. See, all the values in all the 4 cells are high. No value is less than 5. But still it will give the Yates correction, because in all 2 into 2 contingency tables, it gives the Yates correction. Now, this can be done with hand also with the use of a calculator. So, this is the way chi-square test finds application in a lot of experimentation in clinical research. Case control studies, cohort studies, in a lot of pharmacoepidemiological studies, chi-square test is used. It is it is have a lot of potential in pharmacological research, in clinical research, a lot of potential is there. Because we have to do with numbers. We are talking about the number of animals or number of human beings. That is the reason why there is no mean or there is no standard deviation. That is the reason why chi-square has a lot of application in clinical research. So another example, chi-square analysis prevalence of metabolic syndrome in cases and controls. Same research, cases with metabolic syndrome 116, controls 87, marginal total is 203. Without metabolic syndrome is 16, 45, 61. So here chi-square test is 17, probability is extremely low, 0.40 and 23. That means predominantly cases, the dysoriatric people are showing the possibility of a metabolic syndrome, whereas controls are not having that possibility. So this is what is the result. So again, this is the way when you have numbers or frequencies, chi-square test is the test that you have to do. Now I have taken 3 problems from one good standard textbook, Sanchetti and Kapoor, applied statistics, and I told how to do. I am not working out. I am just telling you how the problems come. And some of these problems are taken from question papers. So in question papers, how they give also, I want to tell you. That's what I am trying to tell you. So test whether inoculation is effective against cholera. The figures represent the number of persons. Does inoculation prevent attack from cholera? So this type of question comes practically also, in examination also. So what they have done, into a certain area they have gone and they have inoculated some people. So among the inoculated people, 30 people got cholera. Though they got inoculation, they got cholera. Among inoculated, 160 did not get cholera. Not inoculated, 140 people got cholera. 460 people did not get cholera. So what is the null hypothesis? Inoculation and attack are independent. Inoculation is not effective in preventing cholera. Alternative hypothesis is inoculation and attack are not independent. Inoculation is effective, is preventing cholera. So in null hypothesis, there is no difference between both groups. In alternative hypothesis, there is a difference. So level of significance is 0.05, degrees of freedom is 1. Criterion is table value of chi-square for 1 degrees of freedom is 3.841. Criterion statement is if calculated value of chi-square is more than 3.84, we reject H0, otherwise we accept. So this is how we calculate. 190 into 170 by 790. So what are these? 190 into, this is 190. This is 170. This total is 190. This total is 170. 190 into 170 by grand total. So grand total is 790. Like this you get these are the numbers, you get the expected frequency in each case. So these are the expected frequencies. So this is how you write the table. Inoculated, attacked, inoculated, not attacked. Like this, you write all the observed frequencies in a row, write all the expected frequencies in a row, O minus E whole square, O minus E whole square by E. So you add up all these values to get a total chi-square value of 4.86. Decision. Since the calculated value is greater than the critical value of 3.84, we reject the null hypothesis. Inoculation and attack of cholera are not independent. Inoculation is effective in preventing cholera. See how this has helped in coming to a decision. Maybe the health department in the village is not knowing whether inoculation is effective against cholera or not cholera. By simply finding the numbers and doing a chi-square test in a very simple manner using a hand calculator, you can tell whether this is effective or not. So you can take problems from question papers. They come like this. See, a survey of 320 families with 5 children each revealed the following distribution. Number of boys is given. Is for 5 boys. Say if it is 5 boys, it should be 0 girls. 4 boys means it is 1 girl. 3, 2, 2, 3, 1, 4, 0, 5. So this is like a binomial distribution. Number of families who have 5 boys are 14. This is 56. 3 boys and 2 girls are 110. 2, this is this. Now, is the result consistent with the hypothesis that male and female births are equally probable? You may use the following table giving the values of chi-square. See what they have done. This is how in the question paper they have given. So often paper setters are faced with a problem. Suppose I tell you the chi-square value. Now in this case the degrees of freedom is I think 4, 5, because how many points? 6 are there. 6 minus 1 is 5. So 5. But I tell if I tell I am revealing part of the answer, the student must know to determine the critical value. Student must know the degrees of freedom. So in order not to reveal the level of significance also, for 2 levels of significance, for 3 different degrees of freedom, the question paper setter is giving the values of chi-square. Then what will be done? You write the null hypothesis, alternative hypothesis, level of significance. Computation is by fitting to binomial distribution, taking the probability of birth of female as well as female as 0.5. So you use the binomial distribution here. So you write all observations. First column will be 14, 56, 110, 88, 40, 12. These are observed frequencies. So how do you get the expected frequency for you? For 5 and 0, it will be p to the power of n. The probability distribution formula is p to the power of n plus nc1, p to the power of n minus 1, q to the power of 1 plus nc2, p to the power of n minus 2, q to the power of 2, and so on up to q to the power of n. So this is q to the power of n. This is p to the power of n. Like that, you write the numbers. Expected frequencies are obtained by fitting the binomial distribution. By writing the proper term in the binomial distribution, you get the expected frequency. So you write the expected frequency and you do O minus E whole square by E to get the chi-square value. Let us see another problem. The number of demands for a particular spare part in a shop was found to vary from day to day. In a sample study, the following information was obtained. Monday to Saturday, this is it. Test the hypothesis that the number of parts demanded does not depend on the day of the week. The table value of chi-square for 5 degrees of freedom for 5% level of significance is this. So they have given that degrees of freedom is equal to 5. Here also 6 are there. So 6 minus 1 is equal to 5. So here also the same way, the same type of problem here also given. But here you need not put the binomial distribution. What you can do, null hypothesis, alternative hypothesis, level of significance. Computation is by assuming that the demand for parts on each day is exactly the same. Just like we have done the 7 cities problem. That is the sum of the demands on all the days divided by the number of days. That would be the expected frequency. So you make a sum of all these values. Some value will come. Divide that by 6 to get the expected frequency. That expected frequency is the same for all. Then 124 minus that. 145 minus that, like that you get O minus E whole square by E, and sum of that will give you the chi-square. Now in another problem, out of 8,000 graduates in town, 800 are females. Out of 1,600 graduate employees, 120 are females. See, graduates 8,000 are there, 800 are females, nearly 10%. Out of 1,600 graduate employees, 120 are females. Use chi-square test to determine any distinction is made in appointment on the basis of gender. Value of chi-square at 5% for 1 degree of freedom is 3.84. Obviously, you have to put a 2 into 2 contingency table. So, and then find out null hypothesis, alternative hypothesis, level of significance, finding the table value at the degrees of freedom, that is 1, criterion statement, and finding the expected frequency by the formula chi-square value is equal to, I'm sorry, not the chi-square value, that is the, here you have to write the expected frequency. Expected frequency is obtained by row total into column total by grand total. So all that such type of values added up will give you the chi-square value. So here what you will get, male and female, graduates and employees, and male and female. That's how you will get the 4 cells. From the 4 cells, you have to, by doing row total into column total by grand total, you have to find the expected frequency. Adding up all of them, so you will get the chi-square value. So this is how you work out the different problems. So to conclude and summarize what I have told, chi-square test is a very versatile type of test which is useful in a number of situations. It basically works on the principle that if the deviation between the expected frequency and the observed frequency is more than that, which can be accounted for due to chance, then the difference is significant. So whatever deviation you are observing, whatever difference you are observing between observed and expected should be small, then you can say it is due to chance. If it is more, it is due to a real reason. So depending on the situation, we calculate the expected frequency either by fitting to a distribution or by assuming independence or on the basis of past experience. So how you calculate the expected frequency is the difference between one situation to another situation. So this is the thing, and the books that I have used are D.C. Sanchetti and D.K. Kapoor, Statistics, Theory, Methods and Applications, and Richard A. Johnson, Miller and Friends, Probability and Statistics for Engineers, 6th edition. These two books are very good books. From this, I have taken the material to prepare this PPT and teach you. So thank you for giving me this opportunity. And if you have any queries, feel free to drop a mail either to me at vijaya.ratna@gmail.com or to mybogroup@gmail.com.
Thank you very much, madam. Actually, few of comments they have posted, and rather than questions, and some few questions we can take up from the audience. So as of now, a few questions.
So shall I put escape now and bring it down? Shall I put escape?
Yes, madam. Yes.
Okay.
Yeah, few comments came, madam. Informative and excellent session, ma'am. Thank you, ma'am, for showing how to showing us how to solve the problem. Yes, madam. And one more. So the webinar, a nice webinar, madam. You are great teacher.
Nice webinar.
Yes, madam. Authoritative in the field of pharmaceutical and health sciences. Above all, dynamic. You are former student of Andhra University.
Yes, I remember this student.
Yes, madam. Mostly due to the statistical test, that's why the few questions they didn't ask. So very informative session, madam. On behalf of organizing committee. So we thank you very much, madam.
You put the questions, we'll answer.
Madam, as of now, no one has posted the questions.
Okay, okay, right.
If anything is there, they will post on the the presentation, madam. Directly, they can post the participants those who are having the questions. You can post the above mentioned email IDs.
All right.
Above mentioned email IDs vijaya.ratna@gmail.com and mybogroup@gmail.com. Thank you very much, ma'am. Thank you for your valuable information regarding the statistical techniques and chi-square test, ANOVA. The previous sessions you have given analytical experimentation and chi-square in pharmaceutical experimentation. So all the tests you are giving to all the new students and the upcoming students, research scholars. So we thank you, madam, on behalf of organizing committee. So dear participants, due to time constraint and at the same time the few more comments, so we don't have any questions. I think some questions they didn't post. Madam, one question came. Madam, one question, madam.
Akash Day, ma'am, I have two questions. Can you please explain the main significance of Yates correction in 2 into 2 contingency table, and also 0.5 is added only for number which is greater than
5.
1. No, Yates correction is like this. So this is a continuous type of graph. And why we do Yates correction is, in the case of 2 into 2 contingency table, the degrees of freedom is already only 1. Row minus 1 into column minus 1 is 2 minus 1 into 2 minus 1. Only degrees of freedom is 1. If suppose one cell is having less than 5, number is less than 5 in one cell, then that cannot be used. It is not right to use because of the characteristics of the chi-square curve. We cannot use. Then what we have to do? We have to do pooling. When we do pooling, we lose 1 degrees of freedom. Then it will be 0. That is meaningless. So the minimum chi-square curve, I have showed you curves, is for 1. Even that, actually it is not right. So if you get even less than that, it is not meaningless. That is the reason why statistician 8 has made a correction and said, if you have in 2 into 2 1, always add 0.5 to one cell and reduce 0.5 from another cell. This type of addition and subtraction will correct for the continuity. That is what he said. That is why in the computer, whenever you feed 2 into 2, that is how Yates correction will also come, as I have shown just now. That's what we do.
Okay. Thank you, madam. The student might have understand that concept. Ma'am, as of now, a few more questions were not there. So if any participant having queries, feel free to drop a mail to the Mybo group @gmail.com or vijaya.ratna@gmail.com. So the video will be permanently available in the YouTube channel of Mybo Ishwar YouTube channel. So the participants, whenever they are having queries, they can watch through the Mybo Ishwar YouTube channel and they can watch all the videos. And thank you everyone. We appreciate you are being here. Thanks once again for joining us. We'll see you in next webinar. Keep browse www.mybogroup.com. So thank you very much, madam, for providing for giving your valuable time and valuable suggestions to students. Thank you very much. So now signing off, Sheikh Nasib Basha, Assistant Professor, G. Polarity College of Pharmacy. Along with so we thank to all the organizers and core Mybo group members. To all the members, we are thankful to you. Thank you very much.